All right, this is for AP Physics, distance learning. This should be the video you guys are watching on Thursday. And you need, a couple of you actually have this, but you need the thermodynamics, fluids, physics, the big packet. And the one that we're going to be talking about here a little bit before you read, you're watching this video, hopefully before you read, is the one called thermal physics, okay? So so you got to go to page 169, thermal physics. Okay? Oh, also, before I forget, a couple of things. If you guys have questions, shoot me an email. I'm trying to get back to them as quickly as possible. Hopefully everybody has made contact with some other students in the class to help each other's out. You got to do that. If you need help doing that, let me know. I think most of you have, but if not, just let me know and I'll help you figure out somebody to contact. And then make sure you're checking your answers. A couple of you on the multiple choice, and if after you check your answers you're still confused, let me know. But a couple of you were a little bit off on some of your work. Just a couple of people. There was one person put a note that they were a little confused or whatever. I don't know if that was before or after you checked your work, but after you check your work, if you're still confused, absolutely let me know, because I can make a video on the multiple choice problem or reply back to you depending on how involved the question is. All right. So this is going to be I used to do these old things called guided readings where everybody in the class, like 10 years ago, they got like class MP3 players and I talked and they looked and all that. This is going to be the kind of the video version of that light. Okay, it's not going to be quite as in-depth. But I do need to tell you some stuff about the thermal physics before you read it, okay? And I tried to find some YouTube videos on this section. The stuff on the fluids, it was okay. There were a couple spots where it was like, it's not perfect, but it was certainly good enough for AP Physics. The most, as you can guess, a lot of the issues with the word heat, okay? There's a lot of absolute nonsense in some usually excellent sources of information, okay? Just a quick recap too, when you're reading this, heat as a noun, treated as a thing, they're treating it as a thing, even though it's not, but when they treat it as a thing, you're looking for thermodynamic variable Q, so that capital Q, which is good news, is only in one, I guess technically it's in two, but it's only in one of our equations really, the delta equals Q plus W1, okay? Yes. Okay. Oh, and and this should be on Twitter, but the free response you're going to be doing are going to be based on not this new stuff, but the other stuff, the multiple choice that you guys have already done, the 1 through, I think it was 1 through 6. You're going to be doing free response from the fluids, free response 1, 2, and 3. Free response 1, 2, and 3. Do your best with those. Hopefully you'll get in a group. You'll probably, you have to kind of write your own equation for a couple of them. And actually, while I'm thinking about it, yeah, we'll see how you guys do. Okay, all right. So now the thermal physics stuff. Okay. So first off, this will be the temperature stuff. We will talk about hot versus cold. I just want to let you know that hot and cold is an opinion. Okay. It is okay to say hotter than something because you're doing a comparison and referring to temperature. Something is colder than something else. But if something just says hot or cold, that is vague, right? That's opinion-based stuff, okay? So just a heads up on that. But the temperature section here is pretty good. They'll also address the 0th law of thermodynamics in this first section that you're going to read here in a moment, the temperature section, which I call the duh law. You put two things in contact, after a while they end up at the same temperature, okay? They will be talking about, oh no, that comes in a second. All right, so go ahead, pause the video, read the section on temperature. That's all I had to tell you about temperature. All right, welcome back. So just be able to convert temperatures and have some basic idea of temperature scales, okay? Now, the next couple sections, internal energy, work and heat, first law of thermodynamics, heat transfer mechanisms, okay? We're gonna do all those right now, okay? So internal energy is that capital U that I showed you in the equation the other day, capital U, okay? And for ideal gases, it is gonna be proportional to the kinetic energy. It's not always that simple, but for ideal gases, it will be, okay? And they'll mention things there about solids as well. So work and heat stuff, okay? So they're going to call the stuff heat, okay? And they're going to talk about it being the energy transfer and all that. Again, it's good for you to hear how people are going to phrase this a little bit, so that'll help you to interpret free response keys when we go to practicing actual free response questions. But again, if a question is using heat as a thing, like as a noun, then Q. That's Q. All right. And you'll notice some of my notes on the PDF on the sides about where like this is okay, this is bad, this is good, that kind of thing. You still have to read all of it. Okay, so right now you're going to read internal energy, work and heat, first law of thermodynamics, heat transfer mechanisms, and then you're going to come on back, but wait, don't do it yet, okay? For the first law of thermodynamics, I do want to make you aware that someday you might see delta U equals Q minus W, especially if you're going into engineering. It's just they define, instead of work done on the system to be positive, they define work done on the system to be negative. That's all. It's just like calling up and down positive in a problem that you can still get the same meaning from your answer. But all of our stuff, work done on the system, will be defined to be positive. Okay. Also, in the heat transfer mechanisms, you are responsible for conduction versus convection, and the thermal radiation as well. But I do want to just let you know that conduction, keep things in contact. Convection, still contact, but mixing is playing a big role. So mixing is playing a big role. If the mixing is helping to change the internal energy a lot quicker, typically we call that convection. Okay. Let's see here. Oh, and then yeah, that's it. So go ahead and, one other thing you should do is have your equation sheet out and look at equations as you go so you can see how the AP test writes some of these equations. So go ahead and pause the video and read all the way from where you're at prior, and then stop when you get to ideal gases. All right, hopefully you read that. Now, for ideal gases, okay, you are responsible for what makes an ideal gas ideal. So when you're reading that stuff, actually think about it. Sometimes they have questions specifically to know if you can identify if that counts as an ideal gas. And then there's going to be, for the ideal gas stuff, an equation where they have R equals. Now, when I typically use it, and you've probably seen it before in this form, as PV equals nRT. There are other forms where you use different things besides R, but this is the main one that I will use. And in conjunction with this, there will be an equation that is different from what's on your equation sheet, where I'm going to use U equals 3/2 nRT for internal energy of an ideal gas at a given temperature. Okay, so internal energy for an ideal gas at a certain temperature, and this is the ideal gas law. Do not apply these to liquids or solids, okay? This needs to be applied only to gases, not fluids, just, because that can include liquids, but just gases. This is the ideal gas law, okay? All right, and on scoring guides for free response, and even in recent years, it's being, remember, AP tests are scored by AP physics teachers, people that know what they're doing. They will recognize this instead of the one with the KB in it, okay? So this is an equation that is not on your equation sheet, but there's one that's really close to it, but I still use this one. I prefer this one. Just if you want to use the other one, that's fine too, okay? All right, so let's briefly talk about the ideal gas law, which you may or may not have seen before, okay? P is for pressure. Which you've already learned a little bit about from your fluid stuff, the force over area stuff, okay? Except this is pressure with a surface that's in the gas. I think that was in one of your, the Boltzmann science videos as well. V is the volume of the gas. N is the moles, okay? And you do actually need to know for AP Physics that this is moles of the gas. But remember, moles, I could say 5 moles of people, okay? 1 mole is 6.02 times 10 to the 23rd anythings, okay? So this is just a way to count stuff that's really, really big, okay? If you want to look up why it's that number, you can. There's a reason, okay? But this will be the amount of the gas in terms of like the number of gas molecules in moles, okay? But expressed in moles. Okay, so that's the moles of the gas, okay? So if you're like in a sealed container, the moles can't change, okay? R is the universal gas constant. It's on the equation sheet. It allows us to put equals instead of proportional to. And T, of course, is the temperature. And you'll notice here, okay, if our moles stay the same, there's a lot of things we can start to say here, like U is proportional to T. And then if you start to hold some stuff up here, constant, like V and N, you could even then relate internal energy to like pressure and things like that. So there's going to be lots of times when you're going to need to think about both these equations and what's staying the same, what's changing, stuff like that, okay? Now, there's also going to be PV diagrams. So a couple things here about PV diagrams. We're going to do more with this with the Carnot cycle, probably with the screen recording thing that I do with an animation, either tomorrow or Monday. Let me go ahead and, I'll leave that up here. So let me go ahead and write, here's pressure, here's volume, and they're going to be drawing some lines on there, okay? I'm going to go ahead and just put the Carnot cycle one on here. You're going to see stuff like that, okay? And there's going to be like a process, okay, where you can, that doesn't make any sense, where they can go from here to here, from here to here, from here to here, here to here, stuff like that. That one's actually the Carnot cycle. And on these pressure versus volume graphs, so this is pressure versus volume graphs, or PV diagrams, okay, pressure volume diagrams, you can think of, okay, you can think of dots as temperatures. This is going to help you a lot with the multiple choice we do eventually as well. So if I put a dot on there, a point on this diagram, that means I know the volume and I know the pressure. If I know the pressure and the volume, and if, and this is often the case but not always, and if n is staying the same, guess what? I have the temperature, because I could solve this for temperature. Temperature equals PV divided by NR. Or temperature, if n is staying the same, temperature is proportional to PV. So you take this, you multiply by this, and that's what your temperature is proportional to. So dots on PV diagrams, think of them as temperatures. Okay, so if you put a point on there, think of it as a temperature, assuming that n stays the same. And the vast majority of your problems that have PV diagrams, n will be fixed. Okay, so that is normally the case. All right. So you're going to be dealing with these PV diagrams, and this is going to pop up first in ideal gases, and then again later in the reading when they get to work in PV diagrams. Okay, but I'm addressing it right now. Okay, so let's say I draw a line like this. Okay, if you think about where I went from and to. One pressure times a volume, a different pressure, same pressure times a different volume. This would be a case where my temperature went up. My temperature absolutely changed, okay? Because I had the same pressure, but a different volume. Think about those being multiplied together. This would be a constant pressure process, however. My volume was getting bigger, but my pressure was staying this, wait, did I do that backwards? Hold on a second. My pressure here, my volume here, this would be increasing volume pressure, so pressure stayed the same, but volume increased, so temperature should go up. Yeah, no, that's fine, okay? But this would be a constant pressure process. Just double check and make sure I didn't mess up my algebra in my head there with that. There's not much to mess up, but you never know. All right, and then here's another version. Something you might see on here. Oh, and these got special names. You'll get those in the reading. There's like, there's isobaric, there's adiabatic for when Q is 0. Connect to that here in a little bit. Okay, but here's another one on a PV diagram again, where you can do something like this. Okay, so this is a case, again, similar to this one, except now my volume staying the same. Okay, if I go from here to here, for example, let's say this is my starting point, this is my ending point for my my container of gas, and I go from here to here, this would be my pressure going down, but my volume staying the same, so my temperature would go down. Those are the kind of things, assuming that n is already constant, those are the kind of things you can figure out from PV diagrams. All right, now, there's going to be, again, that's going to tie in mainly to the end. There's going to be some stuff in here as well about getting to that U equals 3/2 nRT. You don't need to be able to derive this, or the one with the constant KB in it, the Boltzmann thing, okay? Boltzmann Constant. You don't need to be able to derive that, okay? They're going to show you the derivation based on the idea of fat ap, which conceptually you're responsible for in terms of the molecules go in, they bounce off, there's a change in momentum, there's a force associated with that, which means that we have a pressure. So for example, you think about the pressure inside my 2 liter here, maybe I shook this up, okay, and the pressure's gone way up because all those bubbles popped and the volume of the liquid stayed about the same, okay? So let's assume I have a higher pressure inside. You can think about the gas molecules hitting, I've drawn a surface here, hitting on the inside of that surface and then coming back. On the outside, hitting off that surface and bouncing back. Well, on that inside, there's going to be a heck more change in momentum on the inside from those molecules hitting on the outside. Bigger outward force than inward force, higher pressure. Okay, so that those ideas of the collisions, yes, the derivation shouldn't need it. And if they did, they'd like do like a part A, part B, part C. They'd kind of, they'd spread it out in a free response question. Okay. Now, the other thing about the PV diagrams, which we're going to do, like I said, more with when we do the Carnot Cycle stuff, is I need one more equation up here. Delta U equals Q plus W. That's delta U equals Q plus W. So these three equations are really important to be looking at when you're trying to figure out the reading on the Carnot cycle stuff. So let's say I have a PV diagram here, so pressure versus volume, PV diagram here. They're going to be talking about the Carnot cycle, and there's going to be this whole big chart. I'll hold it up here for a minute so you know it's right at the end. Okay, there's going to be this chart that goes along with this picture, okay? So this is the nice version of what I'm about to draw. So probably you're going to read this in a minute, but you might want to look at this right now, okay? So for the Carnot cycle stuff you're going to read about, okay, there's going to be these isotherms and these adiabats. So if we want to keep temperature the same, and you can convince yourself on the math if you want, okay, you actually don't need any of the natural log stuff for the AP test. But if we want to keep temperature the same on here, okay, we're going to have a curve like that, okay? Get that little piece on the end. So that's a constant temperature process. That's an isotherm, okay? So that's where the temperature is staying the same. Both pressure and volume are changing, but the temperature is staying the same. They're doing it just right, okay? They're doing this process just right, so our temperature can stay the same. Then there's going to be adiabats, okay? And the adiabats are going to be like this. They're going to be like a steeper curve. And adiabats are where the system is going to be cut off from the surroundings. So your gas that's in your container is completely insulated from the surroundings. With the isotherm, it's allowed to interact with the surroundings. Okay, it's got to keep its temperature the same. But for the Carnot cycle. But for the adiabat, you're going to be cut off. So in other words, in this equation up here, Q is going to equal 0. And this is all going to relate to an animation we're going to take a look at with the piston going up and down. You're going to read about it in here, but it'll make a heck of a lot more sense when we have that. This is your first pass at it. Even if we had in-person class, we would be taking multiple shots at understanding the Carnot cycle. This is just so you can take it. You can start to understand the terminology in the reading. Okay, so this is a case where your delta T will equal 0. The temperature staying the same, and the adiabat where will be Q equals 0. And then here's going to be an isotherm at a lower temperature and another adiabat. And that cycle is going to be really important and would normally be on the AP test and should be again, I would assume. Okay. So this delta T equals 0, what does that tell us when we have isothermal expansion here? Okay. We've got a delta T of 0. Means that if we're talking about our change in U, again, N is fixed for everything I'm talking about right now. For our change in U, it'd be 3/2 NR, the change in T. Well, if our change in T is 0, our change in internal energy is 0, which means when I'm trying to figure out what's going on, because a lot of this is just basic algebra stuff, you're like, oh, if delta T is 0, this is 0. It means this is 0, okay? And then you can start to be like, well, if W has a certain value, like plus 20 or whatever, Q must be minus 20. It's stuff as simple as that, okay? Because they have to add up to 0, okay? For our adiabat here, okay, when our Q equals 0, we're cut off from the surroundings. Because remember, Q is all about molecules bumping into molecules. Molecules of the surroundings bumping into the molecules of the system. But if we're insulated, if we're cut off from the surroundings, Q equals 0, okay? And if Q equals 0, okay, and we have a change in temperature, we'll have a change in internal energy, which will happen, which means we have to have work being done on or by the system, depending on if positive or negative. So stuff like that. So whenever you're trying to figure out that chart at the end, make sure you're looking at these 3 equations while you're doing that. They will help you understand the chart, especially this one and this one, okay? And then there's one more that'll be in the reading, and I think it's the one that you'll be the easiest to deal with, and that is that work done will equal negative P delta V. That work done will equal negative P delta V. All right, and that'll end up being area, and you'll read about that. That's not too bad. So, and we'll connect that to the Carnot cycle with an animation. I think that's going to happen tomorrow. So that's just to get your feet wet with this. So now you do need to read the remainder of this, okay? Everything that's in here is fair game, okay? This is just like the cut to the chase of what's on the AP test. And then we're going to go back and spend some more time, like I said, with the Carnot cycle either tomorrow or Monday, okay? I expect you to have lots of questions, especially on the end of this packet. You may just want to keep a running list of them. And then after we hit this process again and try some of the multiple choice, check them off as you get them answered or figured out. And then the ones that you don't, let me know. Okay. But that's not like an assignment. You don't have to do that. Okay. All right. Entropy. Yeah, you guys can just read. You can just read that. Read entropy. Entropy will just be on there. Just a very basic idea of entropy. Entropy we'll talk more about. No, my AP. When we get to my thermo, we might talk a little bit more about entropy. That's just the part you need for AP, the microstates and macrostates. Second law of thermo. Oh, if anybody's still here, I should mention that this is just a restatement of conservation of energy. It's just the idea that that energy is for an isolated closed system is conserved. So it's just it comes from that. Okay, that's it.